In this problem, we're asked to calculate the instantaneous rate of change for the function at a particular point. The instantaneous rate of change can be visualized by thinking about the slope of the function at that particular x value. This function is a square root function, so it looks something like this. And we are at some x value 3 here. The rate at which this function is changing instantaneously at x equal 3 is equal to the slope of the tangent line that you would get if you placed say a straight edge right up against this function. The slope of that edge would be the instantaneous rate of change. So if you think about how to calculate that, calculating slope usually requires 2 points, but you want the 2 points to be really brought down on top of each other. You can't do that and calculate slope because the run would go to 0, and you can't have the run actually be 0, but you want the run as close to 0 as you can get. So we use a limit. We take the limit as h goes to 0 of the rise over the run. And so this formally defines the derivative of a function. Now we actually want the derivative at x equal 3. So we have two options here. We can place a 3 in directly, right there, and then calculate this. Or we can leave the x in there as a variable and get the answer in terms of x, and then place x equal 3 in. Using the number in the beginning might be a little shorter. The number of algebra steps is about the same, however, and the ideas are all identical. So I'm going to leave the x in there because the formula I get down at the end then would give me the slopes everywhere. And in practice, you rarely want to know the slope at a single value. So we'll go ahead and calculate the slopes everywhere as a function of x, and then use that to figure out the slope at 3 in particular. So we need to set up our difference quotient and then evaluate the limit. And I think what we're going to discover, as we always do in these problems, is that we're going to need to simplify the difference quotient before we can attack the limit. So we need to evaluate f at x plus h. This function returns the square root of 3 times what I give it. So 3 times x plus h is under the root, and then I give it simply an x over here. And so this is the difference quotient that we need to simplify. Now when I'm given a limit of a fraction like this, I gather the clue off to the side. What is the numerator and denominator doing? This helps push me into, helps direct the algebra that I'll end up doing. I notice that as h gets close to 0, the denominator is close to 0. As the h gets close to 0, the numerator will have a root 3x minus a root 3x, and this will be 0. When you're calculating a derivative, that's always going to be the case, 0 over 0. So this means on a derivative calculation, not every limit, but on the derivative calculation, our goal is to find a way to eliminate the 0 causing h's. So this one needs to be canceled with something in the numerator. So we go on a journey here trying to find a way to cancel the h's. And when you're dealing with the difference of two roots, the way to get that h out from under the root is to multiply by the conjugate of the numerator. And you'll see why this works if you haven't seen it before as we multiply this up. The idea there is that the a minus b times a plus b would be a squared minus b squared. So we're using the difference of two squares factors to essentially square these roots, but we're doing it in an algebraically sound way. We're preserving equality in these expressions. So the denominator I'm going to leave alone. It's got the h factored out, so I don't want to multiply that piece out. But the numerator I do want to multiply out so that I get the h out. So multiplying the first term times the first term gives me simply 3x plus h. The cross terms add up to 0, and then minus root 3x times root 3x is minus 3x. And now if we distribute in the numerator, again, let's not distribute in the denominator. In the numerator, I'll have a 3x, a 3h, and a minus 3x. So this 3x and this 3x add up to 0. And I see that everything in the numerator, there's only one thing in this case, but everything in the numerator has an h in it. So I'm going to be able to cancel the h in the numerator with the h in the denominator. That eliminates the problem in terms of the clue, the 0 over 0 problem. And so now we can calculate the limit as h goes to 0. As h goes to 0, the numerator goes to 3. The denominator goes to, let's see, square root of 3x. X plus h will just be x. And this other 3x doesn't change. So I get 3 over 2 square roots of 3x. So in terms of the notation, we would say that the derivative of square root of 3x